Good morning, students, and welcome back to another video lesson from chemistry. The name of the lesson is Structure of the Atom, and today shall be the fifth part of our discussions. In the previous video lesson, we had studied about Rutherfords model of atom. We had seen how, after successfully conducting the alpha particle scattering experiment, Rutherford had proposed the planetary or nuclear model of atom. He opined that the electrons revolve around the positively charged nucleus in circular orbits, and while revolving they are not drawn closer to the nucleus, as force of attraction which is acting towards the nucleus is balanced by the centrifugal force acting away from the nucleus. But this was challenged by Maxwell on the basis of radiation theory. According to this theory, charged particles moving in circular orbits with fast speed emit energy in the form of radiations. Since electrons are also fast moving charged particles, they must release energy continuously in the form of radiations. With reduced energy, they must be drawn closer to the nucleus. Since the loss of energy is a continuous process, the electrons must come closer and closer to the nucleus. Ultimately, they must fall into the nucleus or become its part. However, this does not actually happen. The atom is extremely stable in nature. The size of the atom remains the same, although the electrons are moving in a circular path as stated earlier. Rutherford could not give a suitable explanation for this. The limitation of Rutherford's model of atom was explained by Sir Niels Bohr. He stated that although the fast moving electron is expected to lose energy as radiations, which was suggested by Maxwell, but it does actually lose energy. In fact, out of infinite number of orbits they are that are possible for the electrons, it can revolve only in a certain fixed orbit with definite amount of energy. In other words, the energy of the electron is stationary, or it is said to be in a stationary state. In this state, the electron is not in a position to either lose or absorb energy as radiations. It therefore revolves in the same orbit without losing any energy. This accounts for the stability of the atom. In 1913, Niels Bohr gave a theory regarding the distribution of electrons in the extranuclear space in an atom. The important postulates of his theory electrons revolve around the nucleus with definite velocities in concentric circular orbits situated at definite distances from the nucleus. The energy of an electron in a certain orbit remains constant. As long as it remains in that orbit, it neither emits nor absorbs energy. These are termed stationary states or main energy states. The circular orbits are also known as energy levels or energy shells, as you can see over here. Now, these energy levels or energy shells were also given specific names. They were named as K, L, M, and so on. The order of the energy of these energy shells was K less than L, and L is less than M, and so on. While revolving in an orbit, the electron is not in a position to either lose or gain energy. In other words, its energy remains stationary. That is the reason why these energy states for the electrons are also known as stationary states. So based upon this idea, this is how the model for hydrogen atom was proposed by Sir Niels Bohr. He actually successfully explained certain observations, primarily observation of spectral lines of hydrogen atom. You shall be studying about these in detail in your senior classes, but for the time being, let us quickly understand how Sir Niels Bohr gave a satisfactory explanation for the stability of an atom. As he said that while revolving around the nucleus, the electrons are always in stationary states, and while revolving in these stationary states, they are not gaining or losing energy. Now, as you have seen that electrons distributed in different energy shells are revolving around the nucleus, being charged particles, these are expected to lose or radiate energy. Bohr, on the basis of his experimental studies, concluded that the electrons can lose or gain energy as radiations only in certain fixed amounts or bundles, and that is called quanta. Quanta means measure of energy. Now, in their normal energy state, also called the ground state, the electrons are not in a position to either lose or gain this much energy. Therefore, they keep on revolving in the same orbits known as stationary states. Now, whenever the electron is making a transition, this means it is moving from one energy level to another energy level, then only it can either gain or lose energy. Suppose the electron is moving from the first orbit to the second orbit, so obviously it requires some extra energy. So that much energy has to be gained by the electron. Similarly, when the electron is moving from a higher energy level to a lower energy level, it will lose energy, and that much energy will be lost in the form of a radiation, and that radiation is in the form of a photon. Despite of a very successful explanation for the stability of an atom utilizing the concepts of quantum physics, there were certain limitations. It gave no idea about the shapes of the molecules formed by the combination of atoms. According to the theory, an electron in an atom follows a well-defined circular path called orbit. However, the latest studies have revealed that the path of the electron cannot be followed exactly. It is only of probable nature and not exact as stated by Bohr. However, it is not possible to discuss this concept at the present level. You will be studying about this in your senior classes. Let us now study about how the third fundamental particle of an atom, that is the neutron, they were discovered. Let me tell you that until 1920, an atom was supposed to consist of only two fundamental particles, that is electrons and protons. Since electrons have negligible mass, the entire mass of the atom was regarded as the mass of protons present in the nucleus. Each proton has a mass of 1.67 into 10 to the power minus 27 kg, which is regarded as 1 unit, 1 U. In 1920, Rutherford found that except for hydrogen, the atomic masses of no other elements could be explained by electrons and protons only. For example, the element helium has 2 protons in the nucleus of its atom, and there are 2 electrons in its extranuclear portion. Therefore, the mass of the helium atom must be twice the mass of the proton, but its mass was actually 4 times the mass of proton. To solve this problem, Rutherford predicted that presence of some neutral particles in the nucleus of the atom is a must. Its mass must be the same as that of proton, but it is expected to have no charge. These neutral particles, later named neutrons, were actually discovered by Sir James Chadwick in 1931 when he bombarded a thin foil of beryllium metal with fast moving alpha particles. Each particle was found to have mass equal to 1.675 into 10 to the power minus 27 kg, which is nearly the same as that of proton. However, it did not have any charge, that is, it was neutral in nature. Based upon the experiment, Sir Chadwick found that this neutral particle present inside the nucleus of an atom carried no charge, and its mass was 1.675 into 10 to the power minus 27 kg, nearly equal to that of a proton. So after this very important discovery, the third fundamental particle, that is the neutron, came into existence. So let us quickly study a comparative account of the 3 fundamental particles, beginning with proton, which is symbolized by P or P plus. Mass is 1.67 into 10 to the power minus 27 kg, that is equal to 1 U, and its charge is 1.6 into 10 to the power minus 19 coulombs, which is plus 1 unit. Second is electron, denoted by E or E minus. It has a very negligible mass, that is 9.1 into 10 to the power minus 31 kg. Charge is equal to that of a proton, 1.6 into 10 to the power minus 19 coulombs, but it carries a negative charge, so it is minus 1 unit. Neutron, denoted by N, mass is roughly equal to that of a proton. As you can see, it is 1.675 into 10 to the power minus 27 kg, approximately equal to 1 U, but major difference, it is a neutral particle, it carries no charge. So now we understand that electrons, protons and neutrons are the 3 elementary particles which constitute an atom. These elementary particles do not have any identity as such. Atom is still the smallest particle of matter which is involved in chemical combination with other atoms. Protons and neutrons present in the nucleus of an atom are together called nucleons. Protons and neutrons present in the nucleus of an atom determine its mass. So now we can say that, talking about the composition of atom, we can say that an atom is electrically neutral, that is, it has no charge. In an atom, protons and neutrons are present in the nucleus and electrons in the extranuclear portion. Based upon this understanding, we shall now study 2 important concepts. The first one being atomic number. What is atomic number? Atomic number of an element is equal to the number of protons present in the nucleus of its atom. Like for example, hydrogen. atomic number of hydrogen is 1. It is symbolized by the alphabet Z. So there is one proton in the nucleus of the atom, and as number of protons is always equal to number of electrons, so there is also one electron in the extranuclear space for hydrogen. Actually, the basic definition of atomic number was given by Sir Moseley in 1913. He said that the number of unit positive charges present in the nucleus of an atom is known as atomic number of the element. So, we can say that atomic number given by the alphabet Z is equal to number of protons, which is further equal to number of electrons. Mass number. The discovery of neutrons by Chadwick made it quite clear that the nucleus of an element has both protons and neutrons. Now here hydrogen is an exception, as it has only one proton and no neutron. But for all the other elements, this holds true. Now as the electrons have negligible mass, the entire mass of the atom is that of protons and neutrons present in its nucleus. Since each proton and neutron has mass equal to 1 U, therefore mass of an atom must be the same as the sum of protons and neutrons present in the nucleus. This is known as mass number of an element, and it is symbolized by the alphabet A. So mass number of an element is the sum of the number of protons and the number of neutrons present in the nucleus of an atom. So mass number is number of protons plus number of neutrons, and it is symbolized by the alphabet A. So if we know the mass number and atomic number of an element, we can calculate the number of protons, electrons and neutrons, and also predict the composition of the atom. That is, atomic number is number of protons, further equal to number of electrons, and mass number is number of protons plus number of neutrons. Utilizing this understanding, we can go for the representation of an atom. The atom of an element is generally represented by the symbol of that element. The atomic number is indicated on its lower left hand side of its symbol. See, the symbol is X. Then the atomic number is indicated on its lower left hand side, and the mass number on its upper left hand side. I repeat, the atomic number is indicated on its lower left hand side of the symbol, and mass number on the upper left hand side. Say, for example, sodium. We know symbol for sodium is Na from its Latin name natrium. So atomic number for sodium is 11, mass number is 23. So as you can see, this is the symbolic representation of the atom of sodium. 11 is the atomic number, which is written on the lower left hand side of its symbol, and 23, which is the mass number of sodium, is written on the upper left hand side of its symbol. And as I was telling you, that if we know the mass number and atomic number of an element, we can calculate the number of protons, electrons and neutrons. So from the atomic number, we understand that sodium atom has got 11 protons and 11 electrons. Now that we know the mass number 23, so from this we can calculate the number of neutrons. What shall be the number of neutrons? Mass number minus atomic number. 23 minus 11, that will give us 12. So there are 12 neutrons in the nucleus of sodium atom. One more example, carbon. Atomic number of carbon is 6 and mass number is 12. So you can see there are 6 protons, 6 electrons, and 12 minus 6 is also 6. So there are 6 neutrons. So this is the atom of carbon. So there are 6 protons, 6 neutrons, and 6 electrons. That shall be all for today's video lesson. Thank you.